Time for a pop quiz. Problem solved.
Yeah, we'll start to wind things up right now. I'm seeing that most of the pre...
I'm Mr. Meeseeks! Look at me!
Sorry. I think the audio is coming through on stream. I don't know if that's intentional, Pen. Cool. Yeah, so we are... It's a feature.
No, I'm good to go. I'm good to go.
Okay,
Yeah, I was
sorry.
waiting for one of you to give me the green light.
For sure. I just thought I saw you typing in chat, but yeah. So I think we can probably start moving. So thanks, folks, for coming by. And this is our continuing edition. I can't remember which lecture this is anymore. But I think our last planned joint meeting between the abstract algebra group following Artin and the linear algebra group following Friedberg, Insel, and Spence. And we're culminating that with orthogonal projections and the spectral theorem. Here to lead this discussion is Link. If you have any questions, certainly welcome them. You're free to put them in the text chat here, and I will interrupt Link at appropriate times to let him know what y'all are thinking about. Also, if you are watching over on Twitch, I'll be monitoring that chat as well. Without any further ado, let's get started. Link, take it away.
All right, so we will, I guess, start a bit slower and then ramp things up towards the spectral theorem, which is like one of the biggest things, in my opinion, in linear algebra. Mostly because it's useful not just in linear algebra, but also like in analysis. So, but either way, so the first thing we would like to understand are projections, right? So intuitively, everyone understands projections on some level. I draw a vector here, and you intuitively understand like this would be the projection on the x-axis.
Good morning.
And this on the y-axis.
Good
right?
morning.
But we need to really put words to this intuition. And to do this, we use a handy tool called direct sums, which basically decomposes your space into two subspaces. Right? Here W1 and W2 are subspaces. of V. Now, we call a map. So let me just write on the definition of a projection. Yep. So T is a projection if and only if, or maybe this is by definition, right? So T is a projection if I yeah if V is equal to W1 direct sum W2 and T restricted to W1 is the identity on W1. So what this means is basically T of x1 plus x2 is equal to x1. That's it, right? Or let me be a little more precise here because I do want to be precise. So if V is equal to W1 direct sum W2 and for all W in W1, we have T of W is equal to W, right? So then it's a projection. And so what this is basically saying is if we try drawing things out in 2 dimensions, let's say we are projecting onto like maybe this line. Projecting a vector which is already on this line back onto this line should not change it, right? And that's all this condition says. So I want to decompose my space into 2 subspaces where my map is just the identity on one of these spaces. We don't know what it is on the other space yet. We will show that it's actually 0, but it's identity on one space. And an equivalent characterization is t square being equal to t, right? And we can prove this, right? So we have a theorem. T square equals t if and only if t is a projection. Now, I guess one way would be easy to see, which should be this way. So let T be a projection. Then V is equal to W1 direct
Oh,
sum
yeah?
W2.
Prepare to be iterated.
Oh my God. Yeah. And T of W1 plus W2 is equal to W1, right? So this was our definition of a projection. And we want to show that T squared is equal to T. So let's just hit both sides with T again. So what do we get? We get T of W1 plus W2 is equal to T of W1 plus 0, which is actually just in fact equal to W1 again, right, by definition. So what do we get? We get T square of any W1 plus W2 is equal to W1, which is also equal to T of W1 plus W2. So that T square is equal to T. Now let's go the other way. Let's start from T square equals T, and we want to end up at the fact that T is a projection. Now, a natural candidate for the one of the components of the direct sum, right? We want to decompose V into 2 subspaces. And a natural candidate for W1 would be the range of T. And let me pick a nicer color for this, right? So R of t is by definition all the x such that x is equal to t of v. So it's basically the range of t. So we would want W1 to be the range of t. And we can justify why we are doing this using this identity here. So let's actually go ahead and do this. So yeah. So the range of t is one of our components, and our other component is actually going to be the null space of t, or the kernel of t, which is all the x such that t of x is equal to 0. So we have these two. And I would like to decompose v as the range of t direct sum the null space of t. This is the decomposition I would like to get at. And this kind of makes sense in finite dimensions because we have the famous rank nullity, right? Which says that dimension of v is equal to the dimension of the image in our current notation, R of t plus dimension of the kernel of t. So this is rank nullity. And so just going by intuition, we would want v to decompose this way. And all that's left is to show that this actually works out. So what's left is t restricted to the range of t, right, is actually the identity. And we can see this because is equal to the identity as let x in the range of t implies x is t of, say, some v, right, because it's in the image. Then tx is equal to t square v, but this is equal to tv, which is equal to x. So tx is equal to x for all x in the range. And we're basically done, right? Because now t is invariant on the range. By invariant, I mean it acts as the identity on the range. And it's just 0 on the null space. So t of x1 plus x2, where x1 comes from the range, and this is in the null space of t, is just x1. So it is in fact a projection where v decomposes like this, right? But warning, right? Like this is a big warning. Projections are different from orthogonal projections. And I will define orthogonal projections in a bit. But I feel the need to say this because everything we have intuition for are these guys. Like these are the ones we build a lot of intuition on. And these do not really seem natural to us a priori. But yeah, so now let me define what an orthogonal projection is. Right. Yeah. So T is, I'm just gonna abbreviate this to an OP. If T is a projection and the range of T is perpendicular to the null space of T, right? So again, all of this, we assume we are in an inner product space, uh, as we do in finite dimensions. So again, I need to stress that direct sums do not imply orthogonality. I'm not too sure if this is if the natural thing to understand. Could make this clear. Yeah. So
Hey Link, I can see you drawing right now, but it looks like we just had your mic cut out for a second. Can we test that?
is it better now?
Yeah, I think you're back. Okay.
Okay. Yeah. Could you tell me what's the last thing you heard, maybe, so I can?
We got the V is W1 plus W2, but we didn't get this business about the not the
Yeah.
same.
All right. Yeah. Yeah. So a direct sum does not imply they're orthogonal complements, and this is an example of it, where I take W1 to be the span of the x-axis, or this, and W2 to maybe be the span of something which is not orthogonal to this or parallel, right? And now V is genuinely and honestly a direct sum of these two, like these two subspaces. So V is a direct sum of these two, if this is W1 and this is W2, but they're not orthogonal to each other. So being an orthogonal complement is an added condition on a projection which you add to get an orthogonal projection, right? And we will now prove a sufficient condition for something to be an orthogonal projection, and that is this one. So T is an orthogonal projection if and only if T square is equal to T, which is equal to T star, or the adjoint of T. So in some sense, this takes care of the fact that it's a projection, and this takes care of orthogonality. And intuitively, every time you get confused in any question in linear algebra, you should really just go back to complex numbers, right? So, because what does the second condition tell us in complex numbers? It's what it's telling us is that z is equal to z bar, right? Or the number is real. So in some sense, and enforcing this additional condition, make sure that they are actually perpendicular to each other. And okay, I see how this could like drive intuition away right now, what I just added here, but possibly just remember this and just always compare to complex numbers throughout this discussion, and you'll get more familiar with things. So let's prove this, right? So the forward way, as always, is easier. I mean, not always. So suppose T is an orthogonal projection. Then we have that V is equal to the range of T direct sum the null space of T, and the range of T perpendicular is the null space of T. So this is what we have, and we would like to show that T square is equal to T is equal to T star. So we already have the fact that t squared is equal to t, just from the fact that it's a projection. So all that's left is to show t is equal to t star, right? And the way to do this would be just look at the inner product, x comma, hold on, x comma ty, and I would like to show that this is equal to x comma t star y for all x comma y. So this is the goal, right? Yeah. So, okay. Now we just split x and y into the decomposition we have. So we can write x as x1 plus x2 and y as y1 plus y2, where of course like x1 and y1 are in the range and x2, y2 in the null space. And then if you just compute both inner products, we end up with x1 comma tx1 plus x1 comma tx2 plus I'm so sorry, it's y1 and y2. That's my bad. Plus x2 comma ty1 plus x2 comma ty2, right? So now a few things to notice. Since y2 is in, since x2 and y2 are in the null space of t, or rather, particularly y2 is in the null space of t, this is 0, right? And y1 is in the range of t. That would mean ty1 is just y1 and x2 is perpendicular to y1. So this is also 0. That comes from the fact that the range of t is perpendicular to the null space of t, right? And then x2 and ty2 is again also 0. So we are really just left with x1 comma ty1, which is x1 comma y1. And now let's go ahead and compute the other side, right? So we have x comma t star y is equal to tx comma y, and then just expand it out again. We would get very similar products actually, just with the t on the other side. Let me just write this out. And for, I would say, exactly the same reasons, these all go to 0, and we are left with x1 comma y1, right? So what we have shown is that x comma ty is equal to x comma t star y for all x and y. So that t is equal to t star. Yep. Now we go backwards, which is we have t square equals t star, and I would like to show that t is an orthogonal projection. Another typo there. Yeah. So basically, to show that it's an orthogonal projection, we already have a decomposition of V into the range of T, direct sum the null space of T. We just need to show that the range of T perpendicular is equal to the null space of T, right? So, and we can use the fact that T equals T star, which is what's going to save us here. Because we already used the fact that T square equals to T to get this decomposition. So now that we know T is equal to T star, let's actually compute this. Let's take something in the perpendicular of the range. So let y in R of T perp or perpendicular, and then Ty, comma x is equal to y, comma, know that since T star is equal to T, we just have that this is again equal to y, comma, Tx, right? And now Tx is in the range of T and y is in the range of T perpendicular, implies this is equal to 0, right? So what we have shown is that Ty, comma, x is equal to 0 for all x, which actually means that Ty is equal to 0 and y is in the null space of T. So we have that the null space of T contains the perpendicular of the range, right? And by taking perpendiculars again, like on both sides, because now all that's left is to show the reverse containment, right? We just need to show that the null space of T is also contained in R of T perp, or the perpendicular of the range of T. Yep. And so if you take the perpendicular of both subspaces, what we end up with is R of T double perpendicular contains this, but this is just equal to R of T. So now we know that, actually, you know what, I think this is too much algebra. Let's just do this the old way, which is x in n of t, and I would like to show that x is in R of t perpendicular, right? So let y in R of t, and let's look at this. Y comma x. Now, since y is in the range of t, y is equal to t times y. I mean ty, not t times y, because for all elements in the range, we know that ty is equal to y. So this is equal to y comma t star x is equal to y comma tx is equal to 0, since x is in the null space of t. And this is true for all y in the range of t. So x is actually in the R of t perpendicular, so that P is an orthogonal projection, right? Good. Now that we know what an orthogonal projection is, maybe I give some intuition as to what's happening here. So if you remember the earlier image which I drew, which basically, okay, yeah, actually this is a good time to give you a difference between a projection and an orthogonal projection. So a projection could basically pick these two vectors, it could choose these two vectors as a basis of my two-dimensional space, and then just pick the components along one vector. However, an orthogonal projection always has to pick an orthogonal set of vectors as a basis, and then pick the components along one as a projection. For example, this matrix or this linear map is a projection, but it's not orthogonal. However, this would be something like, I don't know, this is orthogonal. And another handy way to remember when something is orthogonal is if T is an orthogonal projection, then there exists a basis where T is almost the identity in some sense. So these very badly drawn circles are zeros. Yeah. So basically what this is saying is T is basically some part identity and zero everywhere else. And if you think about it, this is really is like a projection. Because if I have, say, a bunch of coordinates here, all this is doing, and say this is M cross M, an M cross M identity. This just picks out the first M elements till xm, and it's zero everywhere else. So in some sense, I just like cut it off, and I'm just projecting it onto the first M elements. And this is the idea for an orthogonal projection. Maybe I need to add something here, an orthonormal basis. Yes. Okay. Now that we know the main ingredients of the spectral theorem, which are orthogonal projections, we can actually deal with the spectral theorem itself. So before we start the spectral theorem, I spend like a few minutes giving some motivation behind it. Not from the physics standpoint, but rather from the math standpoint. So what people realized is if we have a normality, that is, if T commutes with its adjoint, then in some sense, T is basically a complex number. And this is obviously true for complex numbers, right? Because Z commutes with its adjoint. But this need not be true for matrices. And what people realize is if it was true, I can treat it as a complex number. Maybe not one complex number, but like 3 or 4 complex numbers together. And you will see what this means. But the motivation is to greatly reduce studying matrices like these, normal matrices, into what we already know really well, which are complex numbers. And it almost, in some sense, makes it trivial because like complex numbers are really well understood. And so if your linear map is normal, then you understand it really well, and there's not a lot happening there. But it's still very helpful to at least study it, right? So here it is, the spectral theorem. Hmm. So what it says is that if T is normal, that is T commutes with its adjoint, and everywhere like our field of scalars is going to be the complex numbers, and V is a vector space. Oh my God, my handwriting's terrible. Is a vector space over complex numbers. Then it says a bunch of stuff which I will list out, and but like they really all mean the same thing. So in the proof you will see like just proving one of them just automatically implies everything else, right? So then V is a direct sum of subspaces, right? Which hold on, which are all orthogonal to each other in the sense of Vi complement is equal to the direct sum of all the j not equal to I Wj. Oh yes, and I also should mention this that the Wi are eigenspaces. Okay, I'll get into what an eigenspace means in the proof, probably. No, I will do this. And then it also tells us that there exists orthogonal projections, Ti, right? Where the range of Ti is equal to Wi, and further, Ti, Tj is delta Ij, Ti. And this is the Kronecker delta. Maybe this is basically one when I equals to j, and zero every like whenever else. Further, the identity is the summation of all these Ti, I going from one term k. And lastly, T itself is equal to a summation of lambda I Ti, where lambda I is the eigenvalue. I'm just going to write EV here. Is the eigenvalue associated to Wi. Yeah. All right. So let's prove this. So in Friedberg they invoke like a bunch of previous previously done results, which I do not want to do because that seems unfair. So let's prove this, right? So the most important part would be like number one to just give us a decomposition of V into a bunch of orthogonal subspaces, which are in fact eigenspaces. And we prove this by induction, right? So the first claim is we want T to have
a link before we get too deep into this.
Yep.
We've had some success because it seems like there's a delay now between that's making it hard for you to write. We've had some success with like going to a second page.
I see. How do I do this?
Yeah, so if you can see the stream, I think there's like up here.
Yeah.
No, I'm not seeing it actually, so maybe this is moot
Do we
point.
just like start a new?
I mean, that's also an option, but yeah, if you want to do that, we can do that. Otherwise, you can power through here. Just wanted to throw that out there.
Yeah, you know what? It's fine. Like,
Okay.
yeah.
Cool.
Yeah, this is an issue with Algebra, I would say, but it's okay. So we want to do this by induction, right? I want to prove one by. You know what? Actually, let's do this. Let's open a new one.
Okay, sounds good. Pen that's going to involve a slight disruption to the visual.
Yeah, maybe you just open it and send the link on Discord. That would be much.
Okay, I can try to do that.
Okay, so while this happens. Yeah, so I want to talk about possibly some relation to this with analysis, and this is not really important for this, like what's going to happen. So this is why I'm doing it right now. If you do continue studying linear algebra past the finite dimension case, like into the infinite dimension case, the versions of spectral theorem stay true, and it's a lot more helpful there because turns out you can look at linear maps as basically subspaces of the complex plane, which are really interesting, right? Anyway, I guess we are back. Oh, this is so much better.
Okay, this is where we're going to have our visual disruption.
You know what? I should probably just write this down again.
Yeah, just let me know when you're ready, Stuki, and we'll pop up the next share. Sweet. Everything looks good on my side.
Yeah. Excellent. Should be
Yeah.
good.
Okay, yeah. So I'm continuing then. Vi are orthogonal to each other. And let's just do the remaining when we get to them. Let's prove these two are really the core of the proof, right? So we want to prove this by induction. By induction. So we're all familiar with the characteristic polynomial of t, or this guy, the determinant of t minus lambda times identity, right? And this is some polynomial in lambda, which actually splits because remember we are in a complex vector space. So all polynomials split in with complex coefficients. So you have, say, lambda minus lambda 1 into lambda minus lambda 2, so on, all the way up to lambda minus lambda n, right? The lambdas are not distinct. They can be repeated. Yep. Further, we also know that T satisfies this polynomial in the sense of T minus lambda 1i, T minus lambda 2i, so on, T minus lambda n I is the zero map, right? And this is what we know so far. So that means there exists some vector v, which is an eigenvector for t. And how can we see this, right? Basically, look at this entire guy. So either either this is 0 or non-zero, right? So if it was 0, we just continue the induction with this. Continue the argument with this. But let's assume it's non-zero. And this implies that exists v. Let's call this entire thing, let's say, e. There exists v such that ev is not equal to 0, right? Implies ev is an eigenvector for t with eigenvalue lambda 1, right? Because t minus lambda 1 I on ev is equal to 0 implies t ev is equal to lambda 1 times ev. Yeah. So now we know that there exists at least one eigenvector. So let's decompose v into the subspace spanned by ev. Let's call this w1. And the orthogonal complement of w1, right? Where w1 is the span ev. And now what's left is to show that t acts invariantly on this direct sum. And what that means is t is a map from w1 to w1, and it's a map from the perpendicular or the complement to the complement. So in some sense, I can decompose t into two parts, right? In the sense, t decomposes as one part acting on t1 and one part acting on the perpendicular space, where where yeah, hold on. Let me just decomposes like this. In how I like to think about this is that T splits as a linear map, right? So if T is a map from V to V and V splits, in the sense it's equal to W1 direct sum, W1 perp, then T also restricts to individual maps on each space. This is not always the case because it can be that T sends something from W perp back to W1, right? Let me write this down in matrices to make it precise. So if we look at T as some block matrices, and it has the following form. right? Then it acts invariantly on this first subspace of, say, m cross m dimensions, and invariantly on this second subspace of, I don't know, r cross r dimensions, right? So basically, there are no cross terms. The cross terms are zero. And this is what we want to show. We want to show that T acts invariantly on W1, directs on W1 perp. And this can be done because T is normal. Now we need another short proof, I would say, is that, yeah, V is an eigenvector of T if and only if V, this is, if V is an eigenvector of T star, right? In fact, if this is an eigenvector with value lambda, this has eigenvalue lambda bar, or the conjugate. And the proof of this is quite simple. So if T is normal, when T is normal, yeah, T is normal implies norm Tx square, which is Tx comma Tx, is equal to x comma T star Tx, and then we swap things around to get this is equal to, yeah. So if T is normal, then norm Tx is equal to the norm of T star x. Now we look at T minus lambda I. This is also normal, right? Because if I look at the star, it's just T star minus lambda bar I. And since T commutes with T star, T minus lambda I should commute with T minus lambda I star. So now let V be an eigenvector with eigenvalue lambda. Then T minus lambda I V, the norm of this, is equal to 0. But remember, this is equal to the norm of T minus lambda I star V from what we had just shown. So this is also equal to 0. This implies T star is equal to T star V is equal to lambda bar V. So now we can go back to the proof of the spectral theorem, knowing that if V is an eigenvector of T, then V is also an eigenvector of T star. So the setup we were at was V is equal to W1 perp, right? Now T acts invariantly on W1. This is easy to see, right? Because W1 is spanned by an eigenvector of V. Let's call this eigenvector V1, right? Since T V1 is equal to lambda times V1, T is a map from W1 to W1. It doesn't leave W1 in some sense. Now let Y be perpendicular to W1. Then the inner product with V1, comma Ty is actually equal to T star V1, comma Y. And from what we just showed, this is equal to lambda bar V1, comma Y, which is equal to 0, right? So this again shows that Ty is perpendicular to V1, or T is a map from W1 perpendicular to W1 perpendicular. And we're done because V is equal to W1 direct sum a vector space which is perpendicular to W1, right? And T restricts to this subspace, right? And it also satisfies the exact same polynomial as before, which is T minus lambda 1, so on, T minus lambda n is equal to 0 on this subspace. So with the exact same argument, we get another, we can just push out another orthogonal subspace W2 and W2 perp, and then just keep going on until we decompose V into a bunch of orthogonal subspaces, right? And now know that we do repeat eigenvalues. In some sense, we have not yet grouped all the spaces with the same eigenvalue into one, but that is just a trivial step. You do this grouping. It's up to you. Direct sum over distinct eigenvalues. Yeah. And almost by construction. So if you have seen, by construction, the subspaces were perpendicular to each other. Right? Because we started off with W1 and we restricted T to the orthogonal complement. And then we just repeated the process and pushed out another subspace and restricted it to the complement of this. And by construction, we have the second part of the proof, right? Which says that Wi perpendicular is the direct sum of all the j not equal to I. We just have this. And now what's left is to show the third part. Oh, okay. We didn't define the TIs, and it should be pretty natural what oh my god, I'm stuttering, but that's fine. What the TIs are, right? So TI is defined to be the orthogonal projection onto Wi, or T of Wi is equal to Wi, and T of Wj is equal to 0 for all j equal to I, where Wi are in their respective subspaces. And again, this is an orthogonal projection because of part 2, right? Part 2 just gives me the range, which range of each TI. The range of each TI, which is Wi, is perpendicular to the null space, which is all the other Wjs. So we get a bunch of orthogonal projections, which in fact satisfy this as well. Ti Tj is equal to delta ij Ti. And this is true because we can just test this, right? Suppose I is not equal to j, and I put this on some w, then this is equal to Ti Tj Wi plus Wj plus some other irrelevant parts of w, which is equal to Ti of Wj plus 0. Basically, this is in Wj, and this is in the rest of the Wj perpendicular, which contains Wi, right? So, and then this should be 0 because Ti was a projection onto Wi. And this is only true when I is not equal to j. Suppose I was equal to j, we have Ti is equal to Ti, just because Ti was a projection. So we are done. And the next part was that the identity was the summation of the TIs. And now this is because in our proof, we decomposed V into a, a bunch of these Ws. And the only time we had to stop was when the dimension of the orthogonal complement was 0. So in some sense, we exhausted V, right? So the direct sum spans V, and each Ti was a projection onto the respective direct sum. So I of W is equal to W1 plus dot 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 plus Wn, which is also equal to T1 of W1 plus dot 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 plus Tn of Wn, which is also equal to summation Ti of W1 plus summation Ti of Wn. And this is because all the other i's which are not 1 are just 0. And here all the other i's which are not n will evaluate to 0. And then you can factor out the summation Ti and you get W back inside. So we indeed do have identity being equal to the summation of Ti. And finally, we can write down T itself as summation lambda I Ti as each Wi was the eigenspace of T, was an eigenspace actually, not the, was an eigenspace of T. So we just associate say Wi was the eigenspace of lambda, then we can lambda I. Then on Wi, like T restricted to Wi, was just lambda I times Ti, right? Similarly, T restricted to Wj would just be lambda j times Tj. And finally, we get that T is the summation of all these lambda i's, Ti's. I guess a more computational way to see the last part would just be to like hard evaluate this. T of W is T of W1 plus dot 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 plus Wn, which is, these are all the paths in the different direct sum, which is equal to lambda I, Wi, because each one of these are eigenvectors.
Oh, yeah? Prepare to be iterated.
Right? So this is again equal to summation lambda I, Ti, Wi, right? And then we just do the same trick as before, and by just adding like the extra Ti's to get summation lambda I, Ti of W. Yep. And this is the spectral theorem for linear maps in finite dimensions. And this is the part where I told you can, now really comes the fun part, right? Like the uses of this. So earlier I told you if T is normal, as in it satisfies this, I can think of T as a complex number, right? Now the obvious question is like, how do I do this, right? Well, if T is normal, the spectral decomposition gives us that it's equal to the summation of lambda I Ti by the Ti or orthogonal projections. And I can identify T with the complex numbers lambda I, right? In some sense, now if I do T square, it gets associated to the complex numbers lambda 1 square, so on lambda j square. And this is really the entire power of the spectral theorem, where f of t ends up being f of lambda 1, f of lambda j. One easy way to see why this is true for polynomials at least is if t is equal to this summation lambda I ti, then it's basically a diagonal matrix in some good enough basis. Like if you pick the basis of these ti, basically, you get that it's diagonal, right? And we all know that for diagonal matrices, d squared just corresponds to squaring the diagonal. Right? Or in other words, say this is equal to d. Any polynomial applied to d corresponds to p, the diagonal with the polynomial applied to the diagonal elements. And you can use this fact and basically say it's true for all functions, not just polynomials. But this is why, if it's normal, you can really think of the map as a complex number instead of a linear map, because it really is just a bunch of complex numbers, like n complex numbers in this case, right? Now we get a few more corollaries from this, which is basically, I'm not going to number these. I think there are 3 or 4. T is unitary if and only if T normal and the absolute value of the eigenvalues are 1 for all I, right? Now this should actually make sense, because if you think of it as a complex number, the only complex numbers which have like absolute value 1 are on the unit circle, right? And these correspond to your unitary matrices as well. Because if I multiply any two complex numbers in the unit circle with its adjoint, I'm going to get 1. So let me just get rid of this. Yeah. So for the proof, so if it's unitary, then it's obviously normal, and the spectral theorem gives us that T is summation lambda I Ti, but we also have T star T is equal to the identity, but T star T is going to be lambda I bar lambda I Ti summation this. And notice the only reason I could calculate this so quickly was because I just applied the polynomial P of Z is equal to Z bar Z to T, and I just substituted T here. And so I just need to look at it on the eigenvalues. So lambda I bar lambda I Ti, which is what I was talking about earlier, right? So this is equal to summation of mod lambda I ti. This implies mod lambda I is equal to 1 because the identity is, remember, equal to summation ti. So you can just compare coefficients and you're done. And comparing coefficients really does work here because on subspace Wi, Ti is just the identity. But yeah, anyway. Now let's go the other way, which is T normal plus the modulus of lambda I is equal to 1. We can again use a spectral decomposition and just compute T star T, and it's going to be summation lambda I bar lambda I Ti, which is summation Ti, which is identity, because mod lambda I is equal to 1, right? So, like, it's really helpful. Like, thinking of a normal map as a complex number is really helpful. Like, using this is super nice. And later on, like in infinite dimensions, also it's extremely helpful. And we get another corollary, which gives me a condition for self-adjointness, as in T is self-adjoint. Maybe the less I lie, the less I write, the less it lags. So T equals T star if and only if T normal and lambda I Rn R, right? And the proof of this is again extremely easy. We just use the polynomial P of Z equals Z bar, right? Then P of T is equal to summation lambda I bar Ti is equal to, hold on. This is equal to T star, right? Remember
Oh yeah?
Ti
Prepare to be iterated.
star is equal to Ti is equal to Ti square because they're orthogonal projections. And this is again, we're going to do direction probably this way. So now the lambda i's are in R, lambda I bar is equal to lambda I. So this is again lambda I Ti, which is equal to T, and yeah, we're done. And now to go the other way, suppose T equals T star, we do the exact same thing of like comparing coefficients in the sense this is lambda I Ti, while this is lambda I bar Ti. And this is simple. You compare the coefficients lambda and lambda I bar, so we get lambda I is equal to lambda I bar, which implies lambda I is actually a real number. And another way to justify comparing coefficients would be to just take a vector Wi in the subspace and then act both sides on them to get lambda I Wi is equal to lambda I bar Wi implies lambda I is equal to lambda I bar. But like that's an aside. The comparing coefficients is really enough. Oh, yeah. All right. And the the last part is the last corollary. Each of these spectral projections is what we call them. Tj is equal to P of T. Let's call this Pj. Let me rephrase this. There exists a polynomial Pj of Z. There exists a polynomial Pj such that Tj is Pj of T. And how would you do this? We remember T as a sequence of, we associate T to a bunch of complex numbers. So I can construct a polynomial P such that P of lambda j is 1, P of lambda I is 0 for all I not equal to j. And I'm constructing a complex polynomial like this since there are finitely many points here, finitely many values of, and finitely many complex numbers. And then P of T would now be summation P of lambda j Tj, which is now equal to Tj. So all of the eigen projections Tj are actually, oh my god, it's lagging quite a bit now, are actually polynomials of T. Yeah. And this is everything in Friedberg 6.6. If you are here.
Yeah. Well,
Yep.
excellent. Are you wrapping up then?
Yeah, like I'm done, but I'm always open to questions if there are any.
For sure, for sure. Well, thank you so much for being here and laying out Friedberg 6.6 for us. If there are questions, either from the chat or from over on Twitch, feel free to type them in. I will be around for a little while. It sounds like Link will be here for a few more minutes at least as well. Otherwise, for folks who are have been following us on the from the Friedberg group, thank you so much for stopping by. Penn, would you like to say anything about the trend from here?
It has
I see
been a wild and fun ride for our very first like real and true linear algebra reading group in the Simplex server. This is, for me, probably the kind of ultimate end to that particular reading group. And I'll just take the time to give a small shout out to all of our presenters. Thank you again, Link, for today. Thank you, Stuki, for helping kind of co-organize things over the last couple weeks. That's been much appreciated. And we'll continue on. We have a little bit left to do in our real analysis reading group, and Zach and I are probably going to tackle that sometime in April. And we currently have our topology reading group happening over in the Mandelbrot mathematics server. And I'm assuming if you want to shout out the Artin abstract algebra reading group, you guys are going to continue on as well.
Yep, that's right. We're rolling on. So this was part of Chapter 7, most of Chapter 7. And so we'll have a lecture to finishing that up and keep going. We'll go back to our usual time, which is 45 minutes from now, 2 hours later than we started today. But yeah.
Fantastic. So I've dropped a Discord link into the Twitch chat. So if any of those things might have piqued your interest, feel free to follow that chat over to the Elements Discord server, and you can get some more information about the various reading groups that are happening in some of our shared servers here. So with that, I'm going to go ahead and end things on Twitch. Thanks again, Link and Stuki, for the lovely reminder of the spectral theorem.
Excellent. Well, thank you so much.
Anytime.
Yeah, so I'm not seeing questions over on the Twitch side, so that's probably closed up. And I think we can probably wind things down here as well. Link, if you want to do some postmortem, I'm happy to to move over to Simple
Probably
Group.
the only thing I would like to say is that maybe just try doing exercise 6. I found that really nice.
Sorry, exercise 6.
Yeah, exercise 6 in the Friedberg. I mean, like after section 6.6.
Yeah.
I just found exercise 6 to be interesting. That's it. Like, no, I'm not going to do this. Not soon again now.
Yeah, for sure. I'm just pulling it up.
Yeah.
Cool. Right.
All right, folks. So with that, I think we're gonna be winding down for the morning. Throw in a little bit of music here as we wind down. Why? And I have to get ready to go to work. I gotta host bingo today at 2 o'clock, famish. When are we back next? We will be back. Things are a little bit hectic for me next week. Zach and I were hoping to start up our algebra sessions again on Mondays and Wednesdays, but we're going to have to postpone that until April just due to some emergencies that have come up in my mathematics department that I have to attend to. So this coming week, we will probably be doing just some casual mathematics and maybe some casual gaming streams. We've thrown around the idea of maybe doing some Undertale, probably some Zelda in there as well. So it'll be a little bit here and there this week for myself, just because things are a little busy, and then hoping to get back into the more mathematical swing of things as April rolls around. Bingo's usually a great time, I'm not gonna lie. Like, we usually have about 50 or 60 people, and I co-host with somebody, and he's pretty funny. So hopefully he's not hungover today and actually has a sense of humor. Yeah, I've never played Undertale, Stuki, so I'm kind of curious to see what it's like and what that game kind of brings to the table. I've heard a lot of great things about Undertale. Obviously, we listen to the music of Undertale on this channel a lot, and I really dig the music. So I kind of want to actually play it for myself and see what that looks like. So we might start that up next week at some point. So until next time, folks, take care. Is anyone online? We have the Tutor Wizards online, so you can raid over and see what they're up to today. I'll go ahead and get that raid started. I believe that's about that, right? Yep. So, to the best of my knowledge, I believe that they are a Canadian streamer, and I'm not sure exactly what they're working on today, but usually they have been working a little bit on statistics in the past that I've noticed. So let's pop over there, let's say hello to them, and see what they're up to. And if you need a little raid message, there are a couple raid messages there for you guys to copy and paste. So we'll talk to you guys later. I'll be sure to get some notifications out for some of the streams coming up this week if I have some set days and times for those. All right, take care, guys.